Okay, then let's continue our dive into OVN and BGP with the BGP EVPN integration.
Hi everyone, I'm Dumitru, and together with Alesh here, we're going to talk a bit about more BGP and in OVN. This time it's about BGP EVPN and how we try to do a sort of native integration in OVN to avoid complex configurations outside of OVN. So, yeah, I know this is an obvious OVN conference, so I'm not going to insist a lot on how BGP works or what EVPN is, but we do need to at least describe some of the use cases that are relevant to OVN deployments, I guess. So I'll start by doing that, a sort of introduction to BGP EVPN and with OVN at some point. So as you can see in this picture, there's no OVN here. This is a classic network. Let's assume we have a couple of layer 2 networks, let's call them blue and orange, and they're distributed potentially across different geographical locations, right? One of the main use cases for BGP VPN is to actually manage to get traffic from a blue host on this side to a blue host on the other side across a layer 3 fabric. And to achieve that, people use BGP. BGP is a routing protocol that allows routers and smarter switches to connect to each other and exchange routing information. And normally it's unicast routes, but with EVPN, you can also exchange information about layer 2 hosts and the networks they're parts of. And the network is what often gets referred to as the VNI, because one of the common use cases with EVPN is to use VXLAN underneath, and VXLAN has a network ID, the VNI. And in this case, we probably have a sort of spine leaf topology for this geolocation, and then some other location with some other topology, doesn't really matter. We have BGP sessions between all these components here, switches and routers, BGP here, but also BGP across the 2 clouds. And what's relevant is that throughout the BGP peering, we relay information about the 2 networks, about the orange one and the blue one. And a BGP peer here will learn that there are some hosts, some blue hosts or some orange hosts on the other side of the cloud, on the other side of the planet, whatever. And the other way around. And whenever there's traffic that needs to be sent from one side to the other, whenever we cross this layer 2 domain border here, what happens is the packet gets encapsulated into VXLAN. So we have VXLAN tunnels along the way that send the packets to the remote destinations. And here we decapsulate and send it either to the blue host or to the orange hosts, depending on the tunnel we use. So I think a relevant use case is layer 2 broadcast domains that are stretched across IP underlays. Another use case could be seamless moving of workloads across different geolocations. For example, you have this host that runs a service and you need to decommission it because reasons, and you want to move it on the other side of the planet, but you need to have connectivity between other blue hosts that are running here and the new blue host. How does this actually work under the hood? So the BGP control plane, the BGP routers here, the BGP speakers, let's call them because they're sometimes switches. They distribute MAC and IP information per VRF, so per virtual layer 2 network. Those are type 2 EVPN routes. I won't go into the details. It doesn't really matter. They're just MAC and IP information. And this also reduces the need for flooding broadcast packets. And by broadcast, I don't mean actual broadcast necessarily, but broadcasts, unknown unicast or multicast packets, because the top of rack switch here or the BGP speaker here will know that whenever it needs to forward something to Orange on this side, it has to go through this path. Otherwise, it would have to broadcast it to flood it to all its peers. But BGP also distributes IP route information, also per network. Those are the type 5 EVPN routes. In the fabric, I mentioned we use VXLAN to separate the different layer 2 broadcast domains. Yes. Now OVN. If you want to, maybe I should go back. The only difference between these two slides is the fact that I replaced the hosts on the bottom. So now the workloads are actually virtual. So we could actually have OVN deployments at the bottom. A couple of chassis, 2 on the left and 1 on the right, with logical switches, because a logical switch essentially is exactly that, a virtual layer 2 domain, and the local net connection to the fabric. And still have BGP, EVPN, and VXLAN underneath in the fabric. That would work. It'd be fine. But there are some problems. Orange and blue cannot have overlapping IP subnets. Well, they could, but then you need actual layer 2 connectivity between all these top of rack switches here, or you would need some other complex configuration on the top of rack. So that's not always easy. There are also advantages. For example, if a workload here on this chassis needs to speak to another workload in the same network, let's say in the blue network, they can just do it through local net if you have a layer 2 connectivity here, an actual layer 2 physical network. So there's no need to encapsulate east-west traffic. But yeah, what if we do something else? What if we move that line even lower? So the difference now is the orange and blue networks are completely independent if we do this. So okay, let me start with what happened to the tunnels. If you notice, the arrows got bigger. So now the VXLAN tunnels, they don't terminate on the top of rack switch, but instead they terminate somewhere inside OVN. And that means that our orange and blue networks can be completely independent, because it doesn't matter if they have overlapping IPs, it will just work. It's nice because all the traffic processing stays in OVS. So this is a physical host running OVN and OVS underneath. All the processing, including the VXLAN encapsulation, happens in BRINT. And that's nice because we can offload it to hardware potentially. It's also nice because it's data path agnostic, so it just works with both OVS kernel and OVS user space, with or without the PDK, with OVS Docker or whatever, hopefully. And a tiny bit about how this works under the hood in OVN is that in one of the previous talks, someone said OVN requires you to bring your own BGP. That's still the case. You still need to bring your own BGP and run it somewhere on the side, so you need FRR or something to actually do the control plane part, so peer with the fabric. And that means that all the control state information is maintained in the kernel. But what OVN does, similar to unicast routing, it will monitor through NetLink, the Linux constructs, and it will learn where the remote VTEPs are in order to create tunnels in OVS. It will also learn maximum IPs, routes, and so on. It will also be able to advertise the local workloads, so your fabric, potentially other parts that are not OVN, also learn how to reach your workloads. And we move on. We have now a section about how this really works, and that's going to be Alesh's part.
Thank you, Dimitri. May I have? Thank you. All right. So let's take under the hood what is actually happening in OVN when we are talking about BGP and EVPN. So how can we configure that? Well, I have listed 2 options, and is it just that easy? Well, unfortunately, no, it's not. The problem is that in order to actually get all the information that Dimitri talked about, all the remote VTEPs, all the FDBs and the IPs, we actually have some assumptions about the configuration that is provided by the CMS. So that can be seen here on the left side. And I actually made this picture intentional, like 2 parts, because this is highlighting what Dumitru was talking about already. This is highlighting that in order for the traffic to be able to go through EVPN with the OVN integration, we actually don't require any kernel interaction whatsoever for the data plane. For the control plane, we still require running FRR in this case as an agent that will basically provide us with all the information that we need to do the setup in OVN and process the traffic as we should. So just going a little bit into the details, so what we actually need, we need 2 interfaces. We need loopback interface, and we have particular naming right now hard-coded in OVN that might be subject to change, but we need loopback interface, which is LO- and the VNI number. That one is used to advertise static FDBs from OVN. Then we need a VXLAN interface with VXLAN-VNI. That one is used to learn remote VTAPs and static FDBs. And on top of that, we need bridge that is BR-VNI that is basically mastered to those 2 interfaces. And we will use that bridge to learn and advertise IP addresses plus MAC. So that's the whole type 2 routes that Dumitru was talking about. There is one catch that you need to keep in mind when you want to configure that. The VXLAN VNI is actually VXLAN interface that is in the kernel. So you need to make sure that it has a different source port that then will be used for the tunnels used by OVS. Otherwise, there would be a clash, and kernel wouldn't create one or another. Yeah, and those interfaces needs to be in the default network namespace. Okay, so talking about the details, so this is the topology that I will use to describe what is actually happening. So as you can see, we have, like, on the right, we have a host that is just a host without an OVN with one workload that is running FRR with BGP and EVPN advertisement. On the left, that we have, like, some OVN topology. So we have the assumptions that I was talking about on the left, and next to that, we have the OVN topology. So we have logical switch that is configured for the EVPN, and we have some workload connected to that, and we have a logical router with another workload connected through logical switch. So the first step that we actually need to do in OVN, we actually need to learn the remote VTAP. So in this case, the remote VTAP for us means this IP address that is the endpoint of the VXLAN tunnel that we will use to actually connect through. So FRR will learn that. It will populate that on the VXLAN interface. In OVN, we will see that through netlink, and we will create VTAP binding based on that, and VTAP multicast group. The multicast group is there only for the purpose of if we need to do L2 flooding or anything like that. And based on that, we will create open flow rules. As you can see here, we have matching on the tunnel ID, which is the VNI, and the source address. And this is for ingress, if I'm not mistaken, and for the egress, we have the other way around. So we are loading the IP addresses and the VNI and sending it through the OVS tunnel out. One thing that's good to highlight here, this is all local to OVN controller. None of this information will be in any database. So and the reason for that is that each controller might have a different information populated through FRR, and we would have a lot of churn and a lot of information in the southbound database if it all would end up in the southbound database with possibly a lot of duplications. So that's why all of this is in memory in OVN controller. Next thing, we actually need to learn remote FDB. So if we would like to send the traffic from the workload blue W1 into the fabric, we actually need to know the MAC address of the fabric. So again, we will learn that. We will get that from the VXLAN interface. We will create appropriate open flow rules for that. And I think that's about it. Sorry, I forgot to mention, there is also dynamic FDB. So not only that, so if there is a traffic that is coming from the fabric, and it is a MAC address that is not advertised by the BGP, we are actually capable of learning that MAC address, so we don't have to flood it when we actually try to use that from OVN, like on the way back, or if we want to initiate the traffic to that workload as well. Remote IPs, kind of the same story. So again, FRR will populate that on the bridge this time. So this information is on the bridge. And we will again learn that, store that in memory, and create proper flows. One thing to highlight here, this is our way kind of to do ARP suppression, because with this, we won't be sending unnecessary ARPs from the router into the fabric, because we already should know that workload IP address. So we should be able to use that without like sending ARP requests. And then there is the other side. So we actually want to also advertise. So we want to advertise the workloads that we have. This is for the FDB, so this is just the MAC address being advertised. The way it works, that we will take a look what is local to the OVN controller, so what is actually running on a given chassis, and we will put that via netlink to the loopback interface. FRR will pick that up, and it will end up on the other side. So the fabric actually knows that there is a workload with that given MAC address. Same goes for the IP addresses. So again, we will take a look what is local, and we will put that on the bridge this time, not on the loopback. And again, FRR will pick that up, advertise it on the other side, and on the other side you can see there is again the workload can be seen on the other side. And yeah, this is just showcase, like if we do a ping from the blue W1 workload into the fabric. Sorry, actually, this is the other side. This is from fabric to W1. So you can see that it will actually end up encapsulated in the tunnel. So with source being the VTAP, destination being VTAP on the other side, that we have configured through the local IP with proper VNI, MAC address is set, and inside there is the ICMP echo request for the workload from the workload in the fabric. And the replies follows the same way. So the reply will also go through the VXLAN tunnel with proper IPs being set. And behind the logical router port, it's similar. This time we are doing basically the routing inside of OVN as we usually would do. And we will just, again, encapsulate it, send it to the proper VTAP, and VTAP will reply again over the tunnel. Once again, want to emphasize and highlight that this is really data path agnostic. All of this traffic is going through OVS tunnel that OVN will create. Nothing is going through the kernel if it's not necessary. So if you will use OVS DPDK, you should completely bypass the kernel. Yes, and I will hand it back to Dumitru.
So yeah, let's talk about the future. Well, the future is now. This is already implemented for 2603, which is going to be released in March. That's essentially the missing pieces for supporting the layer 3 part of the EVPN story. And if you look at this topology, there's a few differences on the fabric side. We now have a proper layer 3 VRF there. Let's say it's with ID 10. And there's maybe another network, different layer 3 network, reachable on the other side, 8888 here. And on the OVN side as well, we now enable dynamic routing on that logical router connected to the fabric. And we configure some NATs for our workloads or so on. And the nice part is that, well, we will be able to directly learn routes, type 5 EVPN routes that are advertised by the fabric on this logical router. So that means traffic from our internal workloads towards that external network that's maybe on the other side of the world will just work and be encapsulated when it leaves the chassis into VXLAN. If we go to the next slide, this shows a bit how we do the learning part. So learning VTEPs is the same thing. There's nothing special compared to layer 2 case. For learning the routes, the difference is that, so here we see the routes that FRR learned on the OVN side, route 8888. And that translates to a route in the kernel that's in table 10 that OVN controller monitors, and then it creates a learned route in the southbound database. And you saw other presentations about how that part works. So it just works out of the box. We didn't have to change anything. So that means this router now knows how to reach 8888. Now, for the advertising part, we advertise, depending on the configuration, you can advertise the connected networks connected to this logical router. It works the same as regular unicast advertisements for BGP in OVN. We can advertise NAT IPs exactly the same way. So it's supported, was added already in 2503, and it just works with EVPN. And that translates into black hole routes that we saw a couple of times before in other presentations, that FRR sends as type 5 routes to its peers. So now this side of the network, the external 88, can also reach our workloads through EVPN and VXLAN. And I won't go through this because it's almost the same as the other slide. This shows that traffic is actually encapsulated in VXLAN, and it reaches potentially through the NAT that's configured here, the workload that's behind the logical route. Yeah, what other plans we have for the future? The EVPN support is experimental, and we did that a bit on purpose because we wanted to avoid a fork of the BGP implementation in OVN Kubernetes, to be honest. So we would like to reserve the option of changing configuration or the way we implement stuff if that doesn't work for our users. And Alesh mentioned it earlier, we probably need fine-grained configuration on the host side bridge, VXLAN and LUBAC interfaces, because now they're kind of hard-coded. And also, we would really like to hear your opinion, so we can actually make this into a usable feature. And that's it. I don't know if you have questions.
Then thank you very much. Do we have, okay, we have questions. I don't need to ask.
Thanks for the presentation. I want to know if we can use this to have direct connect kind of a feature, wherein a customer who's running on-prem, using OVN, has a subnet, private subnet, and wants to interconnect maybe to AWS or GCP. All are private subnets.
So that's, do you want to take it, or? That's essentially either at layer 2 or layer 3, you can, I guess in your case it's layer 3, right? Because it's a private network.
Yeah.
So it's essentially this diagram here.
If the VMs don't have, let's say, NAT.
Even if they don't have NAT, here, this is your private network. It's connected to a logical router. On the logical router, you can already today configure dynamic routing redistribute connected, and it's going to redistribute this connected network. And then FRR announces it to the fabric, and your other side can be AWS or whatever, some other FRR, some other BGP peer.
So,
so the answer is yes.
You don't need a gateway node, right? Or for this, each compute node can handle that.
Well, yeah, okay. I didn't go that much into the details, but this logical router needs to be bound to a chassis somehow, right? Yeah. So either you have distributed gateway ports configured, or it's a gateway router. Yeah.
Got it. Thank you.
Thank you, guys. I've got a question. Is it possible to announce /32 routes for the connected virtual machines directly from the host that they live on via type 5?
Yes.
And the second question, did you run any scale tests? How many MAC addresses and VNIs can we handle?
Not yet. That's a good follow-up thing to do. Yeah.
Thank you.
Thank you so much for your presentation. On the same slide, you said that in the future you're going to support learning the type 5 routes, right?
Yes. Yeah.
What about advertising the type 5 routes from the logical router, for example?
Yeah, that's also part of it. So it's going to be learning and advertising.
And is it, I mean, and are you planning to support kind of VRF-like architecture on the logical router?
Well, I think, sure. I think VRF Lite will work, but it's not going to be anything explicit in OVN, because OVN is a virtual networking solution. So there's no real point to define VRFs at OVN level, right?
Mm-hmm.
If you need to represent a VRF, you just create a new switch or create a new logical router.
Right. Okay. Thank you.
So you need all those like Linux bridge and Linux slave interfaces under the bridge. That's for control plane, is it?
Yes. Yes, that's for control plane.
Right, and then the VXLAN in-cap decap happens within the OBS through the VXLAN port. So let's say on the right side also you have the similar, there's similar OVN and everything.
Okay.
So now everything is no GNIV, everything is VXLAN. How do you implement OVN ACLs and OVN load balancers and other things now? Like there's no GNIV TLB, and you don't have import, output, all this information, right? So do we lose functionality?
So in this case, you would be talking more like in between clusters connection, right? So you kind of lose some of those information. It should be possible to not connect like.
Let's say it's within the same cluster. Let's say I have a 100 node cluster. Okay,
Yeah.
It's in the same data center. They're within a couple of racks.
Single OVN cluster?
Single OVN cluster. Yeah, single OVN,
Yeah.
100 nodes.
Yeah, in single OVN cluster, you are losing the information that was carried by the GNIV. So that's the.
So no, we cannot do ACLs. We cannot do quite a few things, I think, because.
Yeah, well, that's a little tricky question, but yeah.
I can add on. So there's a way to configure this to give priority to MACs that were learned through BGP EVPN when you do for your forwarding decision. Because in your case here, you would also have OVN. So if you have another workload here, that workload is potentially reachable through VXLAN, but also through GNIV, right? That's why I asked if it's a single OVN cluster. So you can configure this thing to give preference to either go through GNIV for east-west or go through the fabric. If you go through the fabric, sure, you lose logical import information because there's no way to store that in the VXLAN packet. But if you configure it the other way, you can still enforce ACLs.
So what is the use case? Like obviously you guys implemented this because some customer would have asked, right? So is it for provide like did the customer was asking to extend the existing EVPN into OVN, or what was the?
That's one of the cases. So they would like to have any fabric that is connected through BGP EVPN connected to OVN. That's one of the cases that is possible. The other case is that if you imagine OVNK with IC, OVNK IC actually doesn't kind of care about the GNIV information that much. So you can actually use this for OVNK IC mode, and you will replace the GNIV tunnels with VXLAN, and you can connect it through EVPN, potentially with fabric that is not OVN, right? If you want to mix it within the single cluster, yeah, you might lose some information if you would just like to replace GNIV with VXLAN. But if you think about it like OVNK in IC mode, you have the same functionality, basically just replacing the GNIF tunnels with VXLAN.
Yeah. Okay. Yeah. Thanks.
There's another use case though, local net. Local net in OVN assumes you have a layer network that connects all your nodes. If you use VXLAN, you don't need that anymore. You can have layer 3 as your underlink.
Hey guys, thanks for the presentation. I have two questions. So the first question is, with Oven Kubernetes, we're moving to use single VXLAN device instead of multi VXLAN device. So in your one of your slides, you're talking about creating a bridge with a certain name for each VNI, and also doing the same thing for a VXLAN device. So will you support doing single VXLAN device in the future if that's what we're going to go with? Or?
The way we integrate with the host, so with the stuff that's learned by FRR or whatever, by the BGP speaker, is through Netlink. So we need to figure out how those things look like in Netlink world.
Okay.
But it should be doable. Like you can query such devices today through IP commands, right? So then
it's a bridge with a bunch of VLANs on
exactly, yeah. So you should be able to filter per VLAN in that case.
Okay. Yeah. And for my second question was, when you want to use this EVPN feature, do you have to use the BGP feature in Oven?
Depends what you need, right? If you want type 5 routes advertised by OVN and learned by OVN, then yes, you need to use the BGP feature.
Okay.
If it's just to extend your L2 domain, you don't need that. You can just configure the switch to use the VNI, and it will work, and you don't need any other BGP stuff.
Thanks.
I think we're way over.
Yeah, I think so.
Okay. Then thanks everybody.